explainer. You know, every single day, a major city like London or New York flushes tens of thousands of gallons of used cooking oil straight down the drain, creating toxic blockages. But what if I told you that this disgusting waste is actually the high-powered fuel of tomorrow? Today, we're going to explore the fascinating science of bioliquids. It is an incredible journey of engineering and biology that's literally transforming our global energy landscape.
So let's dive right into this surprising question that challenges pretty much everything we know about how we power massive machines. When you look at an airplane or a massive cargo ship, you typically think of fossil fuels, right? That thick, ancient crude oil pumped from deep underground. But what if the fuel of the future is actually sitting right now in a restaurant deep fryer or decomposing in an agricultural field? To really understand how a leftover French fry could theoretically power a jet plane, we first need to define what exactly bioliquids are compared to conventional fossil fuels. In the absolute simplest terms, bioliquids are liquid fuels or energy carriers made from biological materials, things like plants, animals, algae, or organic waste. Now, you might hear the term biofuels, which usually refers to liquids used for transport, like cars and planes. But the broader term bioliquids covers the whole shebang, encompassing fuels used for electricity generation, heating, and cooling in massive power plants too.
To guide us, here is our blueprint for the energy transition today. We'll look at from feedstock to fuel, how bioliquids are made, where they're used, ask if they are really green, and finally, look at the future of energy.
Starting with Section 1, from feedstock to fuel. The evolution of what we actually make these fuels out of, the feedstocks, is absolutely fascinating. First-generation feedstocks rely heavily on food crops. Think corn, sugarcane, or fresh vegetable oil. But advanced second-generation biofuels, they use what we used to literally consider garbage. We're talking municipal solid waste, forestry residues, and agricultural leftovers. And this is a massive deal, because this shift completely removes the competition with global food markets.
Surprisingly, both biofuels for transport and bioliquids for power plants can be derived from the exact same unglamorous sources. Under the European Union's definitions, we can tap into highly sustainable resources, like leftover animal byproducts from the food industry and used cooking oil. We are literally unlocking energy that would otherwise just be totally wasted. In fact, many facilities operate in this brilliant, self-contained closed loop. Processing those animal byproducts takes a massive amount of electricity and heat, but instead of buying fossil fuels to run the plant, these facilities literally burn the bioliquids they extract to power their own industrial gears. It creates this highly efficient, self-sustaining cycle.
Which brings us to Section 2, how bioliquids are made.
So how does this transformation happen? Well, imagine a biorefinery functioning a lot like a massive kitchen. The biomass is your raw ingredient, the processing is your cooking method, and the bioliquid is the finished dish. We have three main pathways. First, fermentation, where microscopic yeast literally digests plant sugars to brew bioethanol. Second, chemical conversion, where oils and fats go through a simple chemical reaction to become biodiesel. And third, thermochemical conversion. For tough, woody biomass, we apply extreme heat and pressure to essentially bake the materials into a dense bio-oil. But science is pushing this even further. Innovations like the European EBIO project are using electricity to stabilize complex, really messy byproducts. They can take incredibly tricky substances like something called black liquor, which is a toxic, sludgy byproduct of paper manufacturing, and run it through an electrolyzer. This effectively upgrades crude liquids into stable fuels that are perfectly compatible with our existing global oil refineries. It's like turning pollution into liquid gold.
Moving on to Section 3, where are they used?
The global biofuels market reached a staggering $150 billion in 2025, driven by a massive surge in policies targeting net zero emissions. And by 2034, that number is projected to more than double to $322 billion. This isn't just some experimental science fair project anymore. We are talking about a massive multi-hundred billion dollar global industry that is replacing millions of barrels of fossil fuels as we speak. Now, why is this so critical? Because liquid fuels are incredibly difficult to replace with batteries in heavy-duty sectors. You simply cannot fly a commercial jet across the Atlantic or power a massive ocean cargo ship using current battery technology. The batteries would just be way too heavy. That is exactly why aviation and maritime shipping are leading this shift towards sustainable aviation fuel and low-sulfur marine biofuels. They provide the incredibly high energy density of traditional fossil fuels, but with a drastically reduced carbon footprint. There's also a huge strategic advantage for terrestrial power generation. Using waste products for renewable heat and power completely bypasses the environmental damage of displacing actual food crops. We get to generate electricity and heat without clearing a single acre of new land or taking food out of the global supply chain.
Take real-world companies like Living Fuels, for example. They managed to rescue 3,000 tons of used cooking oil, stuff that would normally clog up our city sewers, and use it to cleanly generate around 25 megawatts of power. They do this using highly efficient facilities known as combined heat and power plants, which cleverly capture both the generated electricity and the waste heat to warm local buildings all at the same time. Which brings us to a crucial question in Section 4. Are they really green? It's super easy to assume that anything with the word bio slapped on it is perfect for the environment, right? But the answer to this question is actually not necessarily. We have to look incredibly closely at the entire life cycle of these fuels to figure out their true impact. Yes, bioliquids can significantly reduce greenhouse gas emissions. We're often talking a 60 to 85% drop compared to fossil fuels. The main difference is the carbon cycle. Burning fossil fuels takes ancient carbon that was safely buried underground for millions of years and pumps it straight into our modern atmosphere. Bioliquids, on the other hand, recycle carbon that is already actively circulating in our current environment. However, and this is a big however, they only achieve true sustainability if the feedstock is sourced correctly. That means no deforestation, no excessive fertilizer use, and making sure we aren't burning too much fossil energy just to run the manufacturing process. Leading scientific journals constantly monitor the so-called food versus fuel debate. We have to ensure that first-generation biofuels don't inadvertently threaten global food security. In recent years, substantial percentages of global maize, wheat, and vegetable oil crops have actually been diverted to fuel production. If that's left unregulated, it can drive up global food prices. And that is exactly why the transition to second-generation non-food feedstocks is an absolute non-negotiable necessity for sustainable development.
To keep track of all these complex nuances, scientists rely on massive life cycle assessment databases, like the ENA system in Italy. They meticulously calculate emissions from the farm all the way to the tailpipe. By tracking every single input, I mean literally down to the diesel in the tractor harvesting the biomass and the electricity running the conversion plant, researchers can mathematically prove whether a fuel is a net positive for the climate.
And this brings us to a really cool concept, the zero burden approach. When we use residual waste, like agricultural leftovers or municipal sludge, absolutely no environmental burdens are loaded onto the production of that biomass. Think about it. The waste was going to go to a landfill anyway, right? So the environmental cost of growing it stays assigned to its original primary use. The fuel starts with a clean slate, meaning the carbon footprint of the fuel itself remains incredibly low. Let's wrap things up with Section 5, the future of energy. Bioliquids aren't some single magic bullet that will solve everything, but they are absolutely a vital piece of a futuristic zero-waste energy system. They're going to work directly alongside the electrification of our passenger cars and the massive rollout of hydrogen networks. By combining waste and agricultural residues with advanced conversion technologies, we unlock a steady stream of low-carbon liquid fuels specifically tailored for the heavy industries that desperately need them. So I want to leave you with this final thought to ponder today. As aviation, shipping, and global industry continue to expand, how essential will these engineered bioliquids become in our race to build a sustainable planet? The next time you look up at a commercial airliner flying overhead, or honestly even just look at a discarded bottle of cooking oil, you'll know the incredible, untapped potential hidden inside. Thank you so much for joining me for this explainer.